Welcome to today's Explainer. We're going to do something really fun today. We are going to completely demystify the progression of array optimizations and turn those dreaded time limit exceeded errors into lightning fast code. Honestly, if you've ever banged your head against the wall with subarray problems during your data structure and algorithm practice, well, you are in the exact right place.
Here is how we're going to break this down. First, subarrays and brute force. Second, prefix sums optimization. Third, the contribution technique. Fourth, sliding window mastery. And finally, number 5, the optimization mindset. Let's get right into it. All right, section 1, subarrays and brute force, which is really our baseline problem. To kick off our optimization journey, I want you to imagine something. Imagine you're sitting in a high-stakes technical interview. The pressure is on. You're given an input array of size n equals 100,000. Now, how on earth do you find all the subarray sums without your code just completely timing out? It's a super classic scenario, right? And it's one that instantly separates the beginners from the seasoned developers. Now, if you've ever wondered why the obvious answer is usually the wrong one, think about big O growth rates. A brute force approach with an O of n cubed time complexity is literally an immediate death sentence for large constraints. When n is 100,000, calculating n cubed results in a mind-boggling number of operations. Your program will definitely crash and burn before it ever spits out an answer. Before we fix that, let's make sure we are crystal clear on our definitions. The absolute most important rule of a subarray is that it must be continuous. You absolutely cannot skip elements. It's defined purely by a starting index and an ending index. So if you have an array of 1, 2, 3, the sequence 1, 2 is a valid subarray, but 1, 3, no way. That skips the 2, so it's out. So how does the brute force method actually work? Well, it uses 3 nested loops, which redundantly recalculates the exact same ranges over and over again. Loop 1 sets your start index. Loop 2 sets your end index. And loop 3, it just iterates from start to end purely to calculate the sum. This is exactly what gives us that dreaded O of n tube time complexity. We're just doing so much unnecessary repeated work. It's like rereading an entire book every time you want to find a specific quote. Okay, section 2, prefix sums optimization. This is where we start eliminating those nested loops.
What if, instead of starting from scratch every time, we carried forward a running total into a totally separate prefix sum array? That way, we can pre-compute the sum of elements up to any given index. Let's say our original array is 2, 4, 1, 6. Our prefix sum array simply starts with 2. Then 2 plus 4 is 6. 6 plus 1 is 7. 7 plus 6 is 13. We're just accumulating these values sequentially from left to right. It's an incredibly elegant carry-forward optimization. And here is the aha moment. Once you have that prefix array built, any range sum query goes from taking linear time straight to constant time. To find the sum between an index L and an index R, you literally just take the prefix of R and subtract the prefix of L minus 1. That's it. No more looping through the range. We just execute one single mathematical subtraction and we have our answer. By utilizing prefix sums, we successfully strip away an entire loop, taking our time complexity down to O of n squared. Now, full disclosure, we do trade off a bit of space here. We went from O of 1 space to O of n space because we have to store that new prefix sum array. But honestly, in the software engineering world, trading a little auxiliary space for a massive reduction in execution time is usually a fantastic deal. You make that trade every single time. Moving on to section 3, the contribution technique, which is our O of n time optimization. Now, what if the interviewer throws a curveball? What if you need to find the total sum of all possible subarrays combined? If n is 100,000, O of n squared is still 10 billion operations. 10 billion! Your code is still going to time out. So the real question is, can we do this in O of n time without actually generating a single subarray? Yes, we can, and it requires a total shift in how you look at the problem. Instead of calculating things subarray by subarray, we calculate how many times each individual element contributes to the final total. Think about it for a second. An element at index I is going to show up in a bunch of overlapping subarrays. If we can mathematically determine exactly how many subarrays contain that specific element, we can simply multiply the element's value by its total number of appearances. Game changer, right? Here's exactly how you do it. First, you find the number of valid start options to the left of your element, which is just its index, I plus 1, to include itself. Next, find the valid ending options to the right, which is n minus I.
Multiply those two combinations together to get the total number of occurrences for that element. Then, just multiply that occurrence count by the element's actual value. You calculate this for each element, keep a running total, and you're golden.
This elegantly reduces our entire problem down to a single O of n traversal. And the best part, it drops our space complexity right back down to O of 1. We don't even need that prefix summary anymore. We just loop through the original array exactly one time, apply a little bit of basic index math, and we are completely finished. I mean, it is just a profoundly beautiful piece of optimization.
All right, section 4, sliding window mastery. This is for when we're dealing with fixed length subarrays. Sometimes an interviewer will ask you to evaluate subarrays of a very specific fixed length. Let's call it K. Now, the contribution technique we just learned won't apply here, but a sliding window is absolutely perfect. For example, let's say the problem asks you to find the maximum subarray sum, but specifically restricts you to only looking at continuous segments of exactly length 3. I want you to visualize this like physically shifting a picture frame across the array. As you slide the window one step to the right, you simply add the new element coming into the frame and drop the oldest one that falls out. So first, calculate the sum of that very first window of length k. Next, to move the window, you add the newly included element on the right side. Finally, you subtract the element that just got left behind on the left side. By doing this, we are reusing the sum from the previous window and completely avoiding redundant calculations. Instead of summing up k elements from scratch every single time we shift right, we're literally just executing one simple addition and one simple subtraction. The previous window's sum acts as the perfect foundation for the current window.
And this brings us to our final optimized state. We've conquered the fixed-length subarray problem in strictly linear time. The sliding window technique completely eliminates those nested loops, it heavily reuses overlapping calculations, and it operates in highly efficient O of n time and O of 1 space. It's incredibly fast and very light on memory.
Finally, let's wrap this up with section 5, the optimization mindset, or how to choose the right tool for the job. Recognizing specific constraints instantly tells you which mathematical tool to pull from your algorithmic toolkit. As our sources point out, constraints are everything. They tell you the exact boundaries your algorithm has to fit within. So here's your cheat sheet. If you see multiple range queries, pull out prefix sums. If you need a total sum over all possible subarrays, the contribution technique is your best friend. And if you're looking at fixed-length continuous segments, it's time for the sliding window. My challenge to you is to keep this optimization mindset super sharp. Hit those practice problems and see how many redundant loops you can eliminate in your own code. It makes you wonder, what other algorithm bottlenecks out there can you break simply by mapping out constraints and hunting for redundant calculations? The more you practice this stuff, the more these patterns will just jump right off the screen at you. Happy optimizing, and we will see you on the next explainer.